Hi everyone, it's Mr. Zarzak here, and welcome to another edition of Physics Underground. In this episode, we're going to explore the physics of accelerated motion by analyzing the behavior of a ball as it rolls down a ramp. So, let's get started, shall we? Alright, so behind me we have a ramp or an inclined plane. And we're going to take this ball and we're going to let it roll down the inclined plane of the ramp, and then we're going to analyze it. Now, a little historical context. Okay, what we're really interested in getting at is the physics of this right here. Okay, when the object falls, it accelerates or it speeds up. But when it does so, okay, the acceleration of gravity is a fairly large number, at least in terms of when you're trying to analyze it in the 1600s, which is exactly what this guy here was trying to do. This is Galileo. We're going to learn a lot about this guy this year. Because he was really clever, okay, and he was a good experimentalist, and he was also very good at measuring things mathematically to determine relationships, okay. And so what he realized was that by using a ramp, he could reduce the effect of the acceleration of gravity. And by that, I just mean if I take the ball and I let it roll down the ramp, okay, it does speed up as it rolls, all right. But by extending out the length of the ramp and putting it at this angle, the effects of gravity, okay, they're not at full strength. In other words, it still speeds up because of gravity, but the rate at which it speeds up is not as much as if you just drop the ball outright. So then he says, okay, now I've got my experimental setup, now I want to measure. All right, so he takes the ball and he says, okay, let's see how far the ball moves down the ramp with a fixed period of time. Now, the unit of the second, okay, is kind of like the unit of the meter. All right, it's something that we've decided upon. So it's an agreed upon thing, but all units are really just made up. Okay, and so for the timing for this experiment, I'm going to use the time measurement of the Galileo. And I'll show you what I mean. If I take the ball and I release it from the top here, I'm just going to count one Galileo. Okay, and it's good to take multiple trials, so I'm going to do this a couple times. One Galileo. One Galileo. Okay, and I'm just stopping the ball, one Galileo. All right. When I count off to this one Galileo, this 1 unit of time, one Galileo. Okay, so it looks like it goes about here. So I'm just going to take a little post-it note. Okay, and I'm going to put that post-it note right here. Okay, so in this first unit of time, okay, the ball travels this distance. So for a measuring device, rather than use a meter stick or a tape measure, I just thought it'd be a little simpler. I got a piece of paper. Okay, so if I fold it in half, okay, it looks like, yeah, that's actually pretty good right there. All right, it looks like that the ball, actually that's a little bit too long, let me hold it again. That looks really good right there. Okay, so from where I released it to about the center of that sticky note, all right, that's about a distance of 1. Okay, so this is my measuring stick. Okay, so keep that in mind. All right, and it went to about here in a time of 1 Galileo, went this distance of 1 folded up piece of paper. Okay, so now let's do this again, except this time I'm going to count off to 2. Okay, so 1 Galileo, 2 Galileo. 1 Galileo, 2 Galileo. 1 Galileo, 2 Galileo. 1 Galileo, 2 Galileo. Okay, so it's stopping right around here. So I'm going to mark this off again. All right, remember we started at the top here. Okay, and so you can see that the distance that it traveled in this second chunk of time is a greater distance than it traveled in the first chunk of time because the ball is speeding up. It's accelerating as it rolls down the ramp. Let's continue the process, okay? Let's try 3. 1 Galileo, 2 Galileo, 3 Galileo. 1 Galileo, 2 Galileo, 3 Galileo. 1 Galileo, 2 Galileo, 3 Galileo. That seems pretty good right around there. One Galileo, 2 Galileo, 3 Galileo, 4 Galileo. 1 Galileo, 2 Galileo, 3 Galileo, 4 Galileo. 1 Galileo, 2 Galileo, 3 Galileo, 4 Galileo. All right, now that looks pretty good. Let me grab a post-it note. Do this one more time. 1 Galileo, 2 Galileo, 3 Galileo, 4 Galileo. Right about there. Looks pretty good. All right, and I think I can get one more on here, so let's see if we can get to 5. All right, 1 Galileo, 2 Galileo, 3 Galileo, 4 Galileo, 5 Galileo. All right, that seems pretty good. Let me do it again just to make sure. I'm going to mark it now and then adjust it if I need to. All right, so 1 Galileo, 2 Galileo, 3 Galileo, 4 Galileo, 5 Galileo. All right, that's good enough for me. All right, so we can see by the positions of the sticky notes, okay, that the distances that the ball covers for each unit of time get bigger and bigger and bigger because the ball is speeding up as it moves down the ramp. Now, here's the really clever bit. Okay, Galileo designs the experiment, but if we're going to do science, we have to measure, all right? We've got to be able to measure it. Any theory has to stand up to an experiment, all right? So we've done the experiment, so now let's measure, all right? The thing that I'm measuring is the distance between intervals, okay? So this is my arbitrary, this is my distance of 1, okay? This is 1 unit of distance, okay? Now, if I go in between this one and I measure, so here's 1, 2, and 3. Okay, it's gone 3 of these little counts off of the distance, whatever the length of this paper is. So this was a distance of 1, and then this was a distance of 3. Okay. Let's go to the next one. Okay, so here's 1, 2, 3, 4, 5. Okay, now I've counted off 5. So there was 5 of these little measures between here and here. Okay, so there was 1, 3, 5. We're starting to notice a pattern here, aren't we? Okay, and Galileo noticed it too. All right, now we might make a prediction about how far it will be from here to where we marked off down here. It should be 7. Let's see if it is. 1, 2, 3, 4, 5, 6, 7. Look at that. All right, last but not least. So 1, 3, 5, 7. So the distance from here to the last one, shouldn't it be 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, that's not a coincidence. What you're looking at is what's called uniform acceleration. And with uniform acceleration, the distance that you travel each second increases with the square of time. And what I mean by that, okay, is if this is a distance of 1, and this is a distance of 3, and this is a distance of 5, 7, and 9, okay, well, look at the total distance from where we started. From here to here is a distance of 1. From here to here, I go 3 more. 1 plus 3 is 4. 1 squared is 1, 2 squared is 4, okay? This is a distance of 1, a distance of 3, and a distance of 5. 1 plus 3 is 4, plus 5 more is 9. That's 3 squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9. That's not a coincidence. From here to here was 1, 3, 5, 7. 1 plus 3 is 4, plus 5 more is 9, plus 7 more is 16. That's 4 squared. This is 1 squared, that's 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. Let's do the last one. The distance from here to here is 1, 3, 5, 7, and 9. 1 plus 3 is 4, plus 5 more is 9. Plus 7 more is 16, plus 9 more is 25. That's 5 squared. The distance that you travel from where you start increases with the square root of time if your motion is accelerated. Galileo realized this, okay, and wrote the equations that we're going to be working with over the next couple of weeks in class.
Okay, everyone, that brings us to the end of another edition of Physics Underground. So I just want to say thank you for watching this episode on accelerated motion, and we thought we'd leave you with a little bit demonstration. All right, so what we have down here is this disc is one of our hovercrafts that runs on a cushion of air, and our friend Super Bear here is going to take a ride down the hill. So let's do this. Okay, so without further ado, all right.